9.8.
So today, we're going to look at start chapter 14. So we're going to look at sections 14.1 and 14.2 today. So chapter 14, we're going to be talking about bivariate data. The prefix bi means two. The root word variate we'll be talking about variables. This is going to be a situation where you have two variables for every measurement. So like every measurement has like an x and a y to it. So when talking about bivariate data, the major statistic that we're going to be concerned with is called correlation. And this correlation statistic is basically a measurement about the relationship between the two variables. So for all of you that have been using correlation when you've been talking about your hypotheses for these chi-square tests or t-tests or whatever, that is an incorrect usage of the word correlation. So the statistic correlation has a very specific statistical meaning. And the chi-squared or t-test do not test for correlation. We'll talk more today about like what correlation is and what it means and what it shows us and all that jazz. But it is not to be used in conjunction with one of our hypothesis tests we've been talking about. So this word correlation doesn't specify any type of specific relationship between the two variables. So whether they're strongly correlated or weakly correlated, they're still considered correlated. And we have no indication from the measurement or the term correlation, like what that relationship is, whether it's like a linear relationship or quadratic or exponential or some other shape. So to determine any of that stuff, we're going to have to look at something else. So that's kind of where we're going to try to build out today, is kind of talking about that something else piece first. So if we have two variables and we want to talk about the relationship between them, we really should be thinking about the relationship as kind of a cause and effect relationship, because most things in the real world have cause and effect relationships to them. So we want to start by identifying an independent and dependent variable, where the independent variable is like your cause and your dependent variable is like an effect. So for example, let's say our two variables are hand size and height. Which one of those sounds like the independent variable and which one the dependent? Hand size and height.
Independent.
Height is probably the independent variable, and hand size would be the dependent variable, because you'd assume as you get taller, the rest of your body is growing in proportion, right? If you look at your hands as a 3-year-old and your hands as an adult, your hand has gotten much bigger as you've gotten taller, right? And typically you're growing hands and height at the same time, right? Second example, if a company spends more on advertising, will the company sell more of its product? So your two variables are advertising spend and then sales. What's the independent variable there? The advertising spend, right? Because you'd hope that as you spend more on advertising, you're able to sell more product. Now, if you're not, you know, like, it's time to find a new advertising firm, I think. Everybody feel good? Okay. So one of the easiest ways to look at the relationship between two variables is using something called a scatter plot. So the idea is that we're just going to take each data point that has two parts, the independent, dependent part of your variable, and we're going to plot those like we would in x, y. So the independent variable is like your x, the dependent variable is like your y, and we just plot them like we would a point, and we just do that for every piece of data in your data set. Everybody's okay with the idea? So scatter plot's just plotting points, right? So again, we figure out the independent, dependent variables, label and scale your axes. By label, what do we mean? Like give it a unit title, right? If, you know, like we're talking about somebody's IA topic, which is maybe sleep and GPA, your x-axis could be like hours of sleep or minutes of sleep, whatever you maybe decided on. And the other would be, the y-axis would be like GPAs. What do we mean by scale then?
Like how much one going up increases the other.
Perfect, yeah, like the tick marks, right? So if you're talking about sleep and your unit you're using is hours, you might scale it by ones probably, just like 1 hour increments. You guys agree? You know, like 1 hour sleep, 2 hours sleep, 3, 4, 5. It's probably a fair scale. How about GPA though? What might you want to scale GPA by? Well, so GPAs would range from 0 to 5 if they're weighted, sure. But like, what is the tick mark? 0.5 maybe? Maybe smaller, depending on how granular your data is. If you're looking at GPAs from individuals, you may have most of your GPAs between like 3.5 and 4.5. Maybe going by tenths, like 0.1s might be appropriate there, depending on how grouped together your data looks. Everybody's okay with that idea though, when we talk about what we mean by labeling and scaling? Like if you're asked to draw a scatter plot on a test and label and scale the axes, you know what to do. Okay. So, similar to what we did earlier when we analyzed distributions and we used SOCs. Remember, SOC stands for shape, outlier, center, and spread. We're going to do a similar thing with our scatter plots. So what we're looking for on a scatter plot is direction, form, strength, and outliers. And we'll talk about how to find each one of those and the vocabulary we use to describe each one of those as we go. Everybody's okay with that? So the 4 descriptors you're looking for when describing a scatter plot, again, direction, form, strength, and outliers. That's something that sounds like a test question to you, because it sure sounds like a test question to me, right? To be able to describe the scatter plot. And the way you describe it is talking about its direction, form, strength, and outliers. So when we talk about direction, there are 2 answers. It's either positive or negative. So positive direction means that in general your data like trends upward from as you read it from left to right, so it looks like a line with a positive slope. Negative direction means that it trends downward as you read your data from left to right. Looks like a line with negative slope. Everybody's okay with that idea? When we talk about strength of the relationship, you have 4 answers. Well, maybe 5. But you'd say strong, moderately strong, weak, moderately weak, and maybe in a rare instance, no association. But those are like your 5 ways that you could answer the strength of the relationship. The variables are strongly correlated, moderately strongly correlated, weakly, moderately weak, or moderately weakly, weakly, and then like really no association between them at all. And the form will be like your basic function shapes. So like linear, or quadratic, or exponential, or logarithmic, or, you know, your basic function shapes that you would have talked about in your Algebra 2 and pre-calculus courses. So let's look at the scatter plot below here. So if we asked to describe this one, we'd say the strength, it's moderately strong and certainly looks like a shape. The direction is negative because the points will go down as we read from left to right. And the form, that looks kind of curved, possibly like exponential would be my thought. Looks a little bit like an exponential curve. Everybody's okay? In addition, I noticed that there are 2 potential outliers. Looks like one around 2,500 and the other around 9,475. My mouse is. Like these boys right here and right here look like potential outliers to me. Everybody feel good about how we describe a scatter plot using the vocabulary we just talked about? All right, let's do some more example. So again, here is a graph. It looks like for like probably a college football team, looking at the number of points per game and the number of wins in a season. So if we look at this, we'd say the direction is positive because it looks like the graph has it increasing as you go from left to right. Probably strong or moderately strong because it's relatively close. The points look like a distinct shape. And the form would be linear. Looks like a straight line to me. Everybody kind of agree? And I don't really see any outliers there to me. That looks fairly, everything is fairly grouped where I would think it would be. How do you guys feel on that? Is it okay? Again, this should read like a test question, right? Like describe the scatter plot. Basically like the SOX idea again, just a different language because we're talking about a scatter plot as opposed to a distribution. Okay? The next thing we're going to talk about is a line of best fit. So a line of best fit we can use to give a representation of the correlation between the 2 variables. So it's a way to kind of like boil the graph down into a single equation. So depending on how you draw your line of best fit, they could look a little bit different depending on who is doing the drawing. One thing that has to happen though is that line of best fit needs to pass through a mean point. So the mean point is a point, its x-coordinate is the average of all the x-coordinates in your data set, and its y-coordinate is the average of all the y-coordinates in your data set. Any best fit line must pass through a mean point. Everybody okay with that idea? Again, sounds like something that would be part of a test question, right? If I ask you to draw a best fit line, one of the things I would be looking for is making sure that it passed through a mean point. Okay. Next, I want to take a little bit of a moment here and talk about the difference between correlation and causation. So, I've been teaching at this school, I think 18 years, right? In that 18 years, this stapler right here, this one, has been in this room the entire time. Never once have I seen a tiger in this classroom. This stapler repels tigers. You guys believe it? You can buy a tiger repelling stapler. I'll sell it to you. No, what am I doing here?
Correlation isn't causation.
I'm confusing correlation and causation. There's a correlation between the presence of this stapler and the presence of tigers. The stapler is not causing that relationship. What is the nature of that relationship? It's like we're in North America, people. There's not tigers walking around, right? Unless somebody's exotic pet got loose. And that's pretty darn rare, right? If you took this same stapler and you parachuted into like the Indian subcontinent and were counting on this stapler to repel tigers, I think you'd be sorely disappointed on its efficacy. You guys agree? So that's the idea. We want to make sure that we're being very careful with the vocabulary we're using, particularly when we write our IAs. What you will be testing for is correlation. To try to demonstrate causation is very difficult, typically very expensive, and not something that's easily done. It's usually done by like rhetorical means. By that I mean like, I believe that this drug that we're testing is causing this illness to get better. And the reason you're able to make that argument is like, well, you know, this drug has this chemical interaction and this particular pathogen has like this chemical property and the drug is going to attach there and it's going to like target this thing and the immune system's going to respond, and like you can make a rhetorical argument as to why this drug could cause, you know, the person to get better, to be effective against this illness, and then you would have to demonstrate statistically that like there is a correlation there, and there you might be able to infer that that correlation is actually causation because you have some other rhetorical argument as to why this thing would be causing the effect that you're seeing rather than just the two being associated. Does that feel okay? You guys kind of get what I'm driving at there? So in general, the things that we'll be doing in this class, will we ever be showing causation? No, probably not. You might be able to make an argument that there could be a causal relationship, and you could argue why that would be the case. But it would be a rhetorical argument, not a mathematical one. Is everybody good? Okay. So that's that page. Okay, section 2. We're going to talk more about correlation here and like how to maybe tighten that definition up a little bit as to what we mean and how to come up with it. So in the last section we talked about scatter plots and how we can infer strength, direction, and form using a scatter plot. And we talked about like, okay, to describe the strength of that scatter plot, we're basically just using our eyes and looking at how closely the points are grouped together, right? Do you always trust your eyes? Yeah. Could we do better than just using our eyeballs? Yeah, and that's what we're going to be working on doing here today. So what we'd like to be able to do is like quantify the strength of that relationship numerically. So to judge the strength of a linear relationship, I want to emphasize that this is only talking about the strength of a linear relationship. We can use the statistic called the Pearson product moment correlation coefficient, which we abbreviate as PMCC. And we use the symbol R to represent that statistic. Do you guys remember talking about R in your Algebra 2 or pre-calculus courses? You should have. So some facts about R before we move on and talk more about it. So R is a number between -1 and +1. On a test or a quiz, if you give me an R value that's bigger than 1 or less than -1, there's automatically 0 credit for that problem. You've given me an insane person's answer. You'll receive no credit for an answer less than -1 or greater than +1. Everybody okay? Fair warning. Positive R values indicate there's a positive direction. Negative R values indicate a negative direction. Values near 0 indicate a very weak linear relationship. Probably it also implies approximately no correlation between the two variables. That what you have is something that's like a random mess. The strength of your linear relationship increases as you get closer to 1 or closer to -1. So for example, you have one scatter plot with an R value of 0.8 and another one with 0.9. The one with the 0.9 value for R will be more strongly linear than the one with 0.8. And then the values of -1 and +1 occur only if you have a perfect linear relationship. By that, we mean every single data point in your set would be a point that lies on the exact same line. So if you have only 2 points in your data set, every R value calculated is going to be 1 or -1 because you need 2 points to define a line. The line's going to pass through those 2 points exactly. It's going to be perfect every time, right? Any questions so far about R? You guys kind of remember this from your previous courses. It sounded like which was good. Let's keep on going. So what we're going to do here is we're going to convert our values of R into statements of strength. So R values between 0 and 0.5 are weak, very weak. Between 0.5 and 5 are weak. Between 0.5 and 0.75, moderately strong. Between 0.75 and 1, very strong. And notice that the R's in there are absolute values, so the same would be true for like between 0 or -0.25 and 0, we'd say is very weak. And between -0.5 and -0.25, weak, etc., etc. Any questions on that? Would this be something you need to memorize? Yes. Although it should be pretty easy, right? The increments are all just by 0.5s and there's 4 statements. Everybody's okay? I don't think that's too bad. All right. Let's get a little judge or a little build some intuition about what these correlation numbers would look like. So what I've given you here are 6 scatter plots, and I've written in the correlation approximately for each of them. So the first scatter plot is 0 because it just looks like a random blob of stuff. There doesn't look like to be any real noticeable upward and downward trend. It just looks like a random scattering. If I look at the next scatter plot, that's still quite weak, but there does appear to be a little bit of a downward trend. You can kind of see if you look carefully through it. It looks like the graph is kind of trending down from left to right. If you look at scatter plot number 3, it looks a little bit more noticeably increasing. If you read it from left to right, here the R value is 0.5. That's still weak, but getting a little bit better. If I look at scatter plot number 4, the correlation is negative 0.7. Now this thing's starting to look much more like a line with a negative slope. Scatter plot 5, the correlation is 0.9. That's unmistakably looks like a straight line with a positive slope. And the last one has correlation negative 0.99, or I should say R value of negative 0.99. And that is the liniest line we've seen yet, right? That's pretty tightly packed together. Should be unsurprising that that's quite a high linear, or quite a good linear relationship between our data there. Everybody okay? The point of this is just to give you some intuition about what these things would look like. So if you're looking at a scatter plot asked to estimate the R value, you could do a decent job there. Basically, I would be looking for, if I asked you to do this on a quiz or a test, I might give you a range of 0.2. If you're within 0.2 above or below whatever I think the actual R value is, would probably be good enough. So you don't have to be dead on, but you shouldn't say oh, it's negative 0.7 when really it's positive. Or you shouldn't say it's 0.3 when it's really closer to 0.8. You should tell the difference between something like that. But if something is 0.5 or 0.7, that can be tough. So we give you a little bit of wiggle room there. Everybody's okay? So let's do some examples. So here is a scatter plot. Let's start by estimating the value for R here, and then we'll give the direction, form, and strength for the scatter plot. Who feels brave and wants to give me an estimate for the value for R? 0.8. Agrees? Disagrees? It's probably a pretty fair estimate. I think that's all right. Can someone tell me the direction, form, and strength? The direction is positive. That's correct, Katie. The form would be linear. It looks like a straight line. And the strength would be
Very strong.
very strong because we picked an R value in between 0.75 and 1, right? So that is correct. I think the actual R value for this when I did the calculation was 0.8, or rounded to 0.8 anyway, so that was quite a good estimate. All right, let's look at this one. Quite a bit harder here to guess, right? Anybody want to take a stab at it? Give me an estimate for R. I think positive and in the weak range or very weak range is where I would want to be. Yep, I think that's fine. The direction, form, and strength, who can give me somewhat of the direction? There's two possible answers, positive or negative. Positive, because we picked an R value that was positive, right? That's got to match. The form. I would guess linear. I mean, it doesn't look like anything else, right? Just not very strongly correlated. The strength we would say is weak or very weak. I think either would be acceptable here. Everybody feel good? Okay. We look at this one. Who wants to estimate an R for me? Yeah, probably 0 is a decent estimate there, Ellie. That looks pretty random to me. There doesn't seem to be any like upward or downward trend at all with this. So the direction here, say no direction if the R is 0, would be fine. The form, I don't know, you could say linear, I guess, or random. The strength, no association, right, or very weak. I think either would be okay. If you said 0, probably say no association rather than strong or weak. I got one more, I guess. I don't really care anymore. Let's just keep going. All right. Some more facts concerning about R. So correlation makes no distinction between independent variable and dependent variable. So if you do the R calculation with X and Y, if your X is hours of sleep and your Y is GPA, and you get a value for R of 0.7, and then you switch it and do GPA as the X and hours of sleep as the Y, and you calculate your R, you get the exact same 0.7 value. There's no difference between what's independent and what's dependent variable in the R calculation. Sure. The R value will not change if we change the units of measurement. So again, if you're talking about your X's was hours of sleep and your Y is GPA, and it's like, oh man, maybe I should do minutes instead, and you convert all the X coordinates from hours into minutes, your R value will not change. Okay? All right. The R statistic has no unit attached to it. It's just a number. It's not like hours of sleep or GPA units or GPA per hours of sleep or anything like that. It is strictly no unit at all. To be able to do this, both your variables need to be quantitative. You remember when we were doing choosing your IA topic and I hassled you all and denied a bunch of you guys because you had non-quantitative variables? This is why. The R statistic does not describe curved relationship between variables, no matter how strong that relationship might look. So using R to try to decide if something is quadratic or exponential or logarithmic will be relatively ineffective. Okay? You need a different statistic to measure that relationship, and there is another one. And then the last one is correlation is not resistant. That means that it is strongly affected by outliers. So depending on where the outlier is, it can dramatically improve your correlation artificially, or it can really hurt your correlation. Okay? So it can work in both directions. It doesn't, removal of an outlier doesn't mean you're going to improve your correlation. In fact, it could hurt it, depending on where the outlier is. And we'll look at an example here in a moment of that. And lastly, that this correlation is not a complete summary of that two-variable data. All it's doing is describing the linear relationship between the data. There's a lot more possibly going on. All right, so let's talk about how we actually do this computation for R. We'll do this, the expectation is you'd be able to do this by hand in a relatively small example, and be able to do it in your calculator by hand, so be able to show some intermediate steps using the calculator, and just ask your calculator to do it. Okay, we'll talk about examples of how to show all of that later, not today, probably at the start of next class. But here is the formula. So the n in this formula is just the number of observations. So if you take 10 samples, the x1, y1, x2, y2, etc. is just like the x and y from your first sample, the x and y from your second sample, and so on and so forth. So to calculate this, you multiply, or you take x1, subtract the mean from it, divide by the standard deviation for the x's, and then multiply that answer to y1 minus the y mean, divided by the y standard deviation. And you add up all of those for every measurement. And then you take that sum and you multiply it by 1 over n, and that'll give you an R value. Everybody's okay with that? What does that R value have to be between?
-1 and 1.
-1 and +1. Answers outside of that range will receive no credit regardless. So far so good? Okay, and again, we'll work on how to do this calculation in the calculator, by hand, you know, a variety of different ways so you guys can be a little bit more proficient at it. Okay. So remember when I talked to you guys about correlate, or that R, it didn't matter on which variable is your independent and dependent variable. Here's an example. This is the exact same data set. Looks like this is about the value of a used car relative to the miles on the odometer. So notice that when I plotted these, I get two different lines of best fit, but the R value, I guess you wrote it as R squared in this problem, was the same regardless of whether you wrote them as miles, comma, price, or price, comma, miles. Everybody's okay there? And we had mentioned this earlier. So again, correlation describes only linear relationships. Look at these three scatter plots. These look quite different, right? Want to hear something surprising? They all have the exact same R value. What? Again, the point here is that R is not a summary by itself. If you looked at those data, or those scatter plots, I would say probably only two of them you would really call linear in nature, right? The first one and the third one. The second one looks quadratic to me. And the fourth one looks like a bunch of gobbledygook, right? Like a vertical relationship. I don't know what good that is doing anybody, but everybody feel okay? So again, the R value on its own tells you very little about like what is really going on. And in fact, not only do they all have the same R values, this line of best fit would be the same in each of these cases as well. What? I know, shocking. All right, let's talk about the effect of outliers on R values for R. So if you look at this scatter plot, there are two potential outliers. This is about the age of a child and its Gessel score, which has to do with like their vocabulary, I think. So if you look at child 19, that appears to be an outlier in the y direction, correct? Like that point for child 19 in the x is like smack dab in the middle of the x's. That looks like an appropriate x value. But its y is like way higher than all the rest of them. Everybody agree? Child 18 is an outlier in the x direction. Notice it's way outside of the x, the range of x's for all the other points, but its y coordinate is pretty close to the line of best fit, right? Everybody see that? Which one of these do you think is having the most effect on the R? Child 18 or child 19? 18. Is it having is it improving our R or worsening?
Improving.
Yes, it's helping, right? It's helping make the R look better than it actually is. 19, what effect is that having on the R? Is it helping or hurting? That's pure, absolutely hurting. So let's take a look here. So with all 19, our R value is negative 0.64. If I eliminate child 19, our R value improves to negative 0.76. If I eliminate child 18, our R value worsens, really, I don't know that it's a word, to negative 0.33. Does everybody feel okay here? So again, demonstrating that outliers can hurt or help your R value depending on which direction the outlier is in. Outliers in the Y direction are almost always going to be helpful. Outliers in the X direction, harder to say, but they're going to have a bigger impact. Okay, Y direction, typically helpful, less impact. In the X direction, can go either way, but a bigger impact. Everybody cool? That's the takeaway. We add this extra piece of vocabulary. This term is called influential. We say an observation is influential for a statistic. If removing it would markedly change the result. Typically, outliers in the X direction are influential. That's the takeaway here. Everybody okay? Notice in here we've started using this term least squares line and haven't discussed what that means. So just to give you an idea, one way of building your line of best fit is you draw your line of best fit, and then you draw what's called a residual. That's like the distance from the point to your line of best fit. You make that the side length of a square. You calculate the area of that square, and you do that for every single data point. And you move your best fit line so that the total area for all squares is minimized. We found the least possible area. That's one way of building a line of best fit. That's kind of what your calculator is doing when you do a linear regression. It's doing an easier, there's a formula that lets you sidetrack that, but that's kind of what it's doing. So when we talk about a least squares line, that's one way of making a linear regression. Okay. There's a second correlation statistic. So we had Pearson's, the PMCC, Pearson's product moment correlation coefficient. We abbreviate that with the letter R. The second calculation is called the Spearman's rank correlation coefficient. And we abbreviate that with the letter RS, R sub S with this S subscript, or the Greek letter rho. The difference is that the Pearson statistic is good for only linear relationships. It's only going to describe the strength of a linear relationship. The Spearman the Spearman statistic doesn't represent any specific form, but rather it talks about the strength of the increasing or decreasing relationship. So how strongly increasing or decreasing the relationship is. But it doesn't have any respect to form. So it could be linear, exponential, quadratic, whatever. It's only talking about how increasing or decreasing that relationship is. The same facts are true about the Spearman statistic as for the Pearson's. So again, it's always between -1 and 1. Positive Spearman statistics mean that we have a positive direction. Negative means negative. Values near 0 indicate a really weak relationship. The strength of that rank order relationship increases as we move away from 0. And the extreme values, -1 or 1, indicate a perfect rank order relationship. That would mean like for every x, as x gets bigger, the subsequent y gets bigger. And then or for every x, as x gets bigger, the subsequent y gets smaller. So one situation here, let's talk about the relationship between phones and their resale value. So what we have here is the data for one particular brand of cell phone. The x, the independent variable, is the length of ownership, and the y, the dependent variable, is the value lost or the value change for the cell phone over the life of the cell phone. So again, at 0 months, you haven't bought it, there's no change in value. Its value is what it sells for in the store. After 2 months, the price is decreased by 29%, or its value, I should say. At 4 months, it's decreased by 49%, and so on and so forth. So if I went ahead and graphed this is the scatter plot I would get. If I look at this scatter plot, what is the direction here? Negative. And the form looks exponential. And the strength, quite strong, right? That looks like very much like an exponential curve. Everybody agree? It's pretty tightly packed together. Now the R value, is probably in that 0.8 to 0.9 range still, because it's not this doesn't include the steepest part of the exponential curve. That's the least linear part. It's kind of the tail of the exponential. It looks much more linear. So that the R value is still pretty decent. So -0.8, sorry, you should have said -0.8 or 0.9. Oopsie. You understood what I meant. So right in there, strong negative linear relationship. I would say this looks exponential to me, though. But the R value is describing a linear relationship, so we'll say that. We're using the R as our criteria. Okay. So if I want to do the Spearman statistic for this now, we have to look at the rank order relationship. So I have to redo my data from XY's to rank of X, comma, rank of Y. So to do that, we're going to renumber our data from highest to lowest. So what that means is the 20, if I look in the X column, the biggest X value is 24. That would now get rank 1. The next highest rank, or highest X is 22. That would become rank 2. So I renumber the X's, and then all the way down to 13, because there's 13 total data points. And I would do the same thing for the y's. So when I redo that, that's my new xy's. Everybody okay with what I did there? Notice that the xy's didn't change pairings. So the biggest x, 24, is still paired with the smallest y, -87, because 1, the highest rank, x, is paired with 13, the lowest ranked y. Everybody's okay? So I didn't change the pairings at all. All I did was redo the numbers from actual xy's to ranks. Everybody good? Once I've done this, all I need to do now is calculate the PMCC, use the PMCC formula with the rank order data. So the Spearman statistic calculation is the same as the Pearson, but instead of using the raw data, we're using rank order data. So if I went and graphed the scatter plot here for the Spearman, notice that this is very strongly linear, right? The R value here is -0.995. It's like unmistakably a negative sloped straight line. Everybody feel okay there? So far so good? Okay. What is this telling us? That, well, it's really, really strongly that as the longer you own the phone, the less value it gets, right? We can't tell you like the rate at which the value decreases per month. Oh, no. But the longer you own it, the worse off you're gonna be. We can say that. Everybody okay? So it's limited what you can say with it, but still allows you to say something. Even if the data didn't necessarily look linear to start with. Okay. Oh, what if I forgot and I, instead of ranking them highest to lowest, I ranked them lowest to highest? So instead I did this. Guess what's gonna happen? Nothing. Still get the exact same answer. So as long as you don't do like one column highest to lowest and the other column low or highest to lowest, you're going to be fine, right? As long as you pick one way of doing it and do it for both columns, it's going to be okay. Which is nice, right? Like, whoo, it's one less thing to have to worry about. I just got to rank them. Doesn't matter if I do highest to lowest or lowest to highest. As long as I do it to the same to X and Y, we're good. Well, Mr. Kulik, this seems awfully easy. What's the catch? Well, what if there are ties? What do I do with a tie? So let's look at this data set. It's about hours of sleep and grade. If you look at this data set, look at the X's. We have some ties there, right? Notice I have 6.5 occurs 3 times, and 3.5 occurs twice. How do I rank data with a tie? All right, so we'll start by putting them in order from greatest to least. So if I do that, Cindy was the biggest sleeper. She gets a 1. Anton, Lucas, and Julie all had 6.5. They're tied for second place. I'll put those all 2. How many people have I ranked now? 4 individuals, right? That means the next person gets rank 5, which was Jim with 6 hours of sleep. And then Nikki is ranked 7 with 5 hours. I meant Henry is 6 with 5.5 hours. Nikki is 7 with 5 hours. June is 8 with 4.5. Tim is 9 with 4 hours. And then we have another tie. Steve and Kevin are tied for 10th place. There are no ties in the grade category, so I don't have to worry about that. However, this is not what I'm entering in. It's not how I'm going to do the ranking. So those places that were ties, so Anton, Lucas, and Julie, they occupied places 2, 3, and 4. Everybody agree? They occupy 2nd, 3rd, and 4th place. The ranking I'm going to give them is going to be the average of 2nd, 3rd, and 4th place. So I'm going to add up 2, 3, and 4. And divide by 3. So they are going to get rank 3. I'm going to do the same thing with Kevin and Steve, who are occupying places 10 and 11. I will add up 10 and 11 and divide by 2. And their rank they'll get is 10.5. So this at the bottom is the rank data that I'm going to calculate my R value with. Is everybody okay with this? We'll do some practice tomorrow with actual data sets and numbers and stuff, but this is the hardest thing in this chapter, to be honest with you, is making sure you get the ranking correctly and you account for your ties. So once I have the correctly ranked data, I do my R calculation with my rank order data, and I would get 0.814. Notice if I forgot to rank them properly and I just used that first ranking that I went through naively and did, I get a different R value, right? It's 0.814 is the correct version. If I didn't average their places and use that number for the ranking, I get 0.779, and you get a different answer. So you must do that proper ranking to get the correct answer. So compare the two. What's the effect of an outlier going to be? Look at this data set here. If you ignore the outlier, what should the sign of the R value be for Pearson? Negative, correct? With the outlier, look at the R value we get. That's bonkers, right? You get a positive R value just because of that itty-bitty outlier there. What about Spearman? Again, we should still have a negative R value for Spearman, right? Without the outlier? With the outlier, still negative. What's the takeaway? Outliers affected Pearson more than they would a Spearman. Okay? So we want to talk about monotonicity. So we say a function is monotone if it's either increasing or staying the same for all x. And we'd say it's monotone or if it's decreasing or staying the same for all x. So it's like always increasing or staying the same or always decreasing and staying the same. Sometimes you refer to that as monotone up and monotone down. So this Spearman calculation is just a rank of monotonicity. So if I look at these first 3 graphs, notice the first 3 graphs are all increasing or staying the same, correct? Those would all have Spearman statistic equal to 1. because they're all increasing or staying the same. If I look at the second row of graphs, those are all decreasing or staying the same. Their Spearman statistic will all be -1, as they are always decreasing or staying the same. So their rank order data will always be just a full straight on line. Everybody's okay? Will the Pearson statistic be 1 or -1? Only for the last two, right? The ones that are actually straight lines. Everybody's okay? So, poor candidates for Spearman correlation would be things that are not monotonic, so have a definite increasing and decreasing part to it. Like these 3 graphs you've seen here are bad candidates for a Spearman statistic, but Pearson will still be able to talk about the linearness of them, of course. And that's the end of today. You guys should be able to do at this point sections, homework sections 1 and 2. Which are on page 469, 1 through 10, and then 479, 1 through 12. Probably not going to be a lot of computation there. And if you want to wait till next class before starting those, we're going to go through how to do this calculation on the calculator. That's fine. I think you'd be fine in section 1 because I don't think there's any calculation in there. It's just going to be like looking at pictures and describing things. Any questions on what we've done today? So far, so good? Did you also look at the agenda and see what happens? So the A people are taking, what happens for A class on Friday? Quiz. What's that mean for you guys in B section? Monday would be quiz day. So just kind of keep that in the back of your head. Okay? They come fast and furious in this class. We don't mess around. We got a lot of ground to cover. So you blink and it's test time again. Okay. Everybody cool? All right. This is me signing off.